performance libraries that you can find through oneAPI toolkit. So this has been mentioned already. oneAPI comes, the Intel oneAPI comes in toolkits. So the most commonly used for HPC are the one that you find in the base toolkit along with the HPC toolkit. So into that you have direct programming, so languages like Fortran, C, C++, Python, and DPC++, of course, and you have various tools. But what we want to have a look now at is the API-based programming tools that you got, namely the libraries. So those libraries, they are available for C++, Fortran, and C developments. And the one that I will most specifically present briefly here are the Intel MPI library, the oneAPI MKL library, the data analytics library, the collective communication library, and the deep neural network library. So let's get started with the matkernel library. So matkernel library, that is so rebranded oneMKL recently. That is a a library that has been available for years and years from what used to be Intel Parallel Studio. It's probably the most commonly used scientific library that is on the toolkits that you have. It is often embedded into third-party codes and tools, so you might be already using it without knowing it. So this library, so again, it supports SYCL, C, and Fortran compiler. You have it available at no cost and relative free. So this permits, as I mentioned, to have it already embedded into some tools that you may be familiar with. It fully supports CPUs, and some part of are supported on discrete graphics as well. What is very important is there is an internal dispatcher that at runtime assess the level of support of features that your processor is supporting, and that will switch to the most effective version of the functions for your runtime environment. So inside this library, you have dense linear algebra, sparse linear algebra, you have fast Fourier transform, vector maths, random number generators, and statistics, and more. And this permits you to scale from single core to multi-core to multi-socket and through multi-node and clusters, depending on the elements that you are using within the library. So what's inside exactly? So as I mentioned, you have linear algebra, so the very classical BLAS, LAPACK, scale APAC. You have the sparse version of those. You have solvers, then the fast Fourier transform. You have the typical multidimensional fast Fourier transform. There is a FFTW interface to that to simplify the porting of your codes, because FFTW is widely used in many different code packages. You have clustered version of the FFTW, sorry, FFT. You have random number generators, both engine and distribution, statistics, vector maths, which is very important. So all the the typical mathematic functions that you find in the mathematic libraries are directly available in vectorized versions. And you have more like splitting, interpolation, and so on and so forth. So what you can see in this slide is that all of those functions are optimized for CPUs, single core, multi-core. But not only this, what you see in with red lines are fully available directly on the GPU with an interface. And there is a partial support for GPU as well when you have the dotted lines. And when we talk about GPUs, that is Intel embedded GPUs of generation 9 and 12, and or Intel discrete GPUs. A quick presentation on what you can get. So it's, it's just some LAPACK functions. The first is LU factorization, second QR factorization, and the last one is a Cholesky factorization. Those are running on samples on the Xeon scalable processor 9368. That is a 38 cores at 2.4 gigahertz. So what we can see is that going from half the threads on the B-socket machine to the full threads on the same machine permits you typically to multiply by 2 your performance. So really taking advantage of the whole capability of the machine that you are running. So in here, it's purely CPU, right? But it's just for giving you an example. Same thing here, but it's GEM, so general matrix multiplication. But what's interesting here is that it's running on in integer types, so integer 8, integer 16. So those are particularly interesting if you do deep neural network sort of computations. What you can see is running for a quarter of the threads, half of the threads, and the full threads that you have on the machine, so the number of cores, let's say. You have typical linear scaling for all the sizes of the problem that you can have, but the very first one to the smallest one, obviously the overhead of multi-core multi-threading becomes too large when you for the full size of the full number of cores that you have available. But you can see that very, very quickly you have extremely good performance. One small caveat on this slide is that those are integer operation, and the slides are tagged as flops. So it's not flops, it's integer operation, but nonetheless. So that was it for this very, very quick presentation of the oneMKL. So let's present now the oneDAL, that is data analytics library. So oneAPI data analytics library, so OneDL, it's a library that helps speed up the data analysis by providing highly optimized algorithmic building blocks for all stages of data analytics, that is pre-processing, transformation, analysis, modeling, validation, and decision-making. Computation, they can be performed in batch, they can online, and even in distributed processing mode. The library is optimized for data ingestions along with algorithmic computation to increase the throughput and the scalability. The library is directly integrated into the Python libraries. So meaning that if you have your usual Python program that is loading the module that it needs, it will take advantage directly of OneDL because it's part of the Python binding. Now, if you are users of scikit-learn, Spark, Apache Spark, of XGBoost, then you can download special versions of those tools, which will have OneDL integrated into them, and getting the full benefit of the acceleration that the library is providing you. So here are the algorithms for data transformation and analysis that you have on the library. As you can see, all of them are working on batch, and some of them are specially optimized for distributed processing, and a few of them are also optimized for Intel GPUs. You have the same for the machine learning algorithms. Again, all of them are working on batch, and some permits you to have distributed processing and or optimization for Intel GPUs should they be integrated or discrete. So again, very, very quick presentation of this oneDL. So now let's have a look at the oneAPI deep neural network library named oneDNN. So the particularity of this one is that it helps developers to improve the productivity and the performance of their deep learning application. It uses the same API to develop both for CPU, GPU, or and use whatever is the most useful for you at a given time. What is very important is that this library is fully open source, so you can download the sources, you can review them, you can enhance them, and propose further optimizations that will potentially be integrated into the main repository. That's exactly, for example, what happened with Fujitsu and Riken, who proposed some optimization for running on the Fugaku supercomputer, and so those have been integrated into the main tree, and this permit Riken to run, I think it's like a 9-time improvement compared to their previous workload, which is great. So what you have on this oneDNN library, so you have algorithms that are optimized for either compute intensive operation, memory bandwidth limited operation, and data manipulation. Those are supporting the C++ and DPC++ compiler. That they are optimized for Xeon processor and also for Gen 9 and Gen 12 GPU from Intel. Okay, again, I feel like I'm rushing it, but I only have 15 minutes, so sorry. Let's get going. So a quick presentation of the Intel MPI library. So Intel MPI library, so it's one of the building block of the HPC toolkits that has been available for years through Parallel Studio and now oneAPI. So this library gives you a very seamless interface for getting access to any sort of underlying networks, should they be Ethernet, OmniPass, InfiniBand, RoCE, shared memory, and any network that supports the Open Fabric interface. So it's really rely on the OFI for the low level functions. The library itself is particularly optimized for collectives with specific algorithms and taking advantage of many hardware optimization available on the underlying networks, especially for InfiniBand. You got native interface and native performance. That means that you get the whole, as good a latency as you can expect, and the full bandwidth, and you also are reducing the memory requirements for your transmissions. What is really useful also is that you have a plenty of runtime improvement that you can take advantage of when using your binaries built on top of this library for pinning, so process pinning, and also GPU pinning for the GPU part. And you have the interface with OpenMP that is really well managed. And so on the latest library, you have a lot of improvement for, especially for Mellanox connectics and with the various type of version of the interconnect like FDR, EDR, HDR. And yep, I think that's it. Not much to say. It's really a very important building block for parallel processor, parallel codes. And last but not least for this one is the oneAPI collective communication library, oneCCL. So this is a communication library that is really oriented towards machine learning and deep learning frameworks. So permitting to take advantage of multi CPU, multi GPU, multi nodes without the bother of going through further parallelization through MPI. But the interesting thing is that the library itself takes advantage of MPI and or the OFI API for performing this parallelization. So meaning that you get all the benefit of OFI and MPI for your scalability. So that really gives you very high level of scalability for your machine learning and deep learning codes. Yeah, I think that's it for this presentation. Sorry for me rushing, but yep. If you have any question, happy to take them.
Thank you so much, Gilles.